Okay, once you're ready, then please tell me, I will start.
You can start.
Okay. Good morning, everyone. I'm Mr. Saqib Murtaza, and with my other group member, his name is Mr. Daulat Khan, and we both are doing work with Professor Dr. Kumkumam. Today we are here to present one of our research collaborations, and the title of our research collaboration is Unraveling the Mechanics of Fractal Fractional Nanofluid Model via Integral Transform Technique and Zakian's algorithm. This is the presentation's layout. Primarily, we will discuss research background, and then we will shift to the literature review, novelty in the study, objectives of the study, significance of the study. And in the next sections that will be presented by Mr. Daulat Khan. And finally, he will summarize this research collaborations with the summary of our analysis, and he will give some future directions to the future upcoming researchers. So let's start from the research background. The very basic terminology in our research area is fluid dynamics. Because we are working in computational fluid dynamics, so we must have some knowledge about the fluid dynamics. It is a study of fluid's motion and its behavior. And it has many applications everywhere around the universe. We can see some applications in ocean tides, weather patterns, air conditioning systems, and wind turbines. And the whole fluid dynamics theory, we use these three fundamental equations. The first one is Navier-Stokes equations, which is used for the velocity of the fluid. The second one is Fourier law of heat, conduction, convection, and radiations, which we use for the heat transfer analysis. And the third one is Fick's law. This law is used for the concentration analysis. The second basic term is fluid. Fluid is a substance that deforms continuously under an applied shear stress. And we have two classes of fluids. The first one is Newtonian fluid, and the second one is a non-Newtonian fluid. Yes, please.
Can you open your camera?
Okay. Sure. It's okay now?
Thank you so much. Yeah.
Welcome. So we have two classes of fluids that are dependent on Newtonians of viscosity. The first one is Newtonian fluid, and the second one is non-Newtonian fluid. So the fluid which obey the Newtonian law of viscosity that comes in Newtonian fluid, and the second one is non-Newtonian fluid which do not obey the non-Newtonian fluid. Now the question is that what is Newtonian law of viscosity? So we have the statement of this law in bullet form that when shear stress is linearly and directly proportional to the shear strain, then we called it Newtonian law of viscosity. Now those fluids in which the relation between shear stress and shear strains is linear and direct, then we called it Newtonian fluid. Example of fluids, we have water, air, paint, honey, and oil, etc. These are some examples of fluids in which some of them are Newtonian fluids and some of them are non-Newtonian fluids. But in our study, we considered a diathermic oil. So let's see that what is diathermic oil. Diathermic oil, also known as a thermal oil, and it is a type of heat transfer fluid that is used in industrial applications to transfer heat between a heat source and a heat sink. It can operate at higher temperatures without boiling or freezing. Nanofluid. Nanofluid is a heat transfer fluid that contain a nanometer-sized particles. And this experiment or this fluid was firstly successfully attempted by Choi and Eastman in 1995 at Argonne National Laboratory, USA. And we have different shapes of nanoparticles. We have bricks, spherical, cylindrical, and plates. And you can see many studies on these shapes of the nanoparticles in the literature. On the basis of nanoparticles, we have different types of nanofluids. Unary nanofluids. Unary nanofluids are those fluids which contain only one nanoparticles in the base fluid. Binary hybrid nanofluids are those fluids which contain two different nanoparticles in a single base fluid. Ternary hybrid nanofluids are those fluids which contain three different nanoparticles with one base fluids, and so on. But the question is that why we use nanofluids. It has many features, but few of them are we have on the screen. It enhances the heat transfer, reduce the size and weight, improve the lubrication properties of the many lubricants. It improves the stability of the fluid. We use in industry for cooling purposes. In renewable energy systems, we use in heat exchangers, and to keep cool the electronic devices, we use these kind of nanofluids. We do our analysis by using fractional derivative tools. So we must have a bit knowledge about the fractional derivative and its origin. It is a generalization of classical derivative with non-integer order. And history related to the question that when on 30th September 1695, Leibniz asked from the L'Hopital that what should be the consequences if we choose the order of the derivative 1 by 2. So he replied that it seems a paradox, but if we work on this question, so we will get some fruitful results. And now after that, many mathematicians work on this derivative and these topics, and we have many fruitful results in the literature nowadays. It is recognized by many researchers that fractional calculus is an efficient tool to describe complex and real-world problems, including viscoelastic material, fluid flow, diffusive transport, probability, electrical network, and electromagnetic theory. In the literature, you can see many fractional operators, but we will mention few of them which are well-known and mostly used in the literature. The first one is Riemann-Duval fractional derivative. Then we have Caputo fractional derivative. The advanced version of Caputo is Caputo-Fabrizio fractional derivative with exponential kernel. Then Atangana and Bellino came and he advanced it more with Mittag-Leffler functions, and they presented an AB fractional derivative. Now in recent Atangana in 2016, they combined two different types of calculus, and he presented a fractal fractional calculus with three different types of derivatives. So in our analysis, we are going to use the fractal fractional derivative. For our model, we read many literature papers, but few of them are here, which are the base papers. And from these base papers, we get the idea. The first one was discussed by Nadeem Ahmad Sheikhs in 2021. He used a fractal fractional model for the MHD flow of Casson fluid in a channel. Then Daulat Khan presented a new idea with a fractal fractional derivative with power law kernel for convection heat transfer in a channel flow between two static upright plates. The next base paper is my own paper, and I also utilized the same idea which was used by Nadeem Ahmad Sheikhs and Daulat Khan. And I presented finite difference simulations of fractal fractional model of electrosmotic flow of Casson fluid in a micro channel. So these are the base papers in which we take help and presented a new mathematical model. This paper is novel on the basis of these terminologies that we consider fractal fractional model, concentration equations, polystyrene nanoparticles in kerosene oil. And we solve this model by integral transform technique. And for the simulations, we use numerical Zakian's algorithm. So these are the things which makes our paper new. These are some objectives of the study. To formulate and obtain the solution of natural convection nanofluid flow, to show that the fractal fractional model describes the flow behavior better than the classical model, to explain the behavior of embedded parameters on the generalized nanofluid's velocity, temperature, and concentration, to study the applications and general uses of nanofluid in a modern technology, to show the rate of heat and mass transfer of the regular fluids by adding nanoparticles in them. These are significance of the study. When we achieve our objectives, then our results will be helpful in the following sections. The results obtained from this research will help to enhance the knowledge of fractal fractional model and nanofluid flow. It will be a base for complex nonlinear flow problems recurrently taking place in engineering and applied sciences. It will help us to understanding physically trends and features of various nanofluid flow. Fractal fractional models will provide deep study about the rheology of a fluid's flow as compared to the fractional and classical model. This is the research methodology, and we adopted to solve our mathematical model. Primarily, we proposed a problem, and then we model it mathematically along with initial conditions and boundary conditions. The mathematical model was initially in dimensional form, so we used some non-dimensional entities to make the system non-dimensionless. After making it non-dimensionless, we used the fractal fractional approach to make it generalize in terms of order of the derivative. Then we solve it by integral transform technique. For the numerical simulations, we use numerical Zakian's algorithms, and we draw some graphs for the embedded parameters and discussed it physically with physical arguments. And finally, we conclude our analysis. From this step, I will invite my other group member, Mr. Daulat Khan, and he will start the presentation of this seminar. So Mr. Daulat Khan, please.
Okay, thank you, Thaqib Murtada, for your nice introduction and starting. Okay, from this time, we will start the problem formulation. So first, we have the, this one is a vector form of the velocity which we take, and it is clear from this equation that the velocity is a unidirectional and one-dimensional. And similarly, we have the vectorial form of a concentration and temperature equation. Next. This is the Navier-Stokes equation, which is the basic equation for our modeling, and in which we adopt the body forces, which represent in equation number 3. And we have magnetic field effect, which is represented in equation number 4. By putting equation 3 and 4, we get the our main equation. And this is the nanofluid correlation as we consider a nanofluid in our mathematical modeling. So this is the dynamic viscosity, density, and the whole correlation of the nanofluid. Next. We take a polystyrene nanoparticle with the base kerosene oil-based fluid. So this is the thermophysical property which we take from the literature, because these are familiar in literature. So we take these physical property from the literature. After putting the equation number 2, 3 in Navier-Stokes equation, we get the final velocity equation in the form of equation number 7, in which see that this NF represent the nanofluid. We take the nanofluid in this main equation. Equation number 8 represent the heat equation, and equation number 9 is represent the concentration equation. And this is the novelty that we first time take for the such problem, and for the fractal analysis, we take the concentration equation. Next. This is the boundary condition. From here, we can see that initially the velocity of the fluid at time equal to 0 is equal to 0, and while the at y is equal to 0 means the right plate of the model is also static, while the the left plate is static, while the right plate of the model is moving with constant velocity. And this is the temperature equation. Initially, the temperature is ambient temperature, and the plate temperature is ambient, and while the left temperature is a temperature of the surrounding, and similar on the concentration profile. Next. This is the geometrical illustration of our model. We can see here from the figure that we have two parallel plates, and the fluid is between in these two parallel plates. And these are the boundary condition on the left plate, and these are the boundary condition of the right plate. And we see that the left plate is static, while the right plate is having a constant velocity in the direction of x, and the flow is the direction of x, and the flow is due to the heat transfer and the moving of the right plate. This is the dimensionless variable we use for dimensionalization to dimensionalize our model. Next. By incorporating equation number 11, which is the dimensionless variable, we get a dimensionless form of our mass equation in the form of equation number 12, which is the dimensionless form of momentum equation, equation number 13, which is dimensionless form of the heat equation, and equation number 14, which is the dimensionless form of the mass equation. Dimensionalization help us to reduce our time, and we have too easy for the calculation to find the solution. Next. And this is the dimensionless form of the initial boundary condition. Next. During dimensionalization, we get a dimensionless parameter. The first one is thermal Grashof number, the second one mass Grashof number, Prandtl number, and Schmidt number. After dimensionalization, we need to generalize our model. In this time, we use the fractal fractional derivative operator to generalize our model. So we apply the definition of fractal fractional derivative to the equation of momentum equation, heat equation, and mass equation, in which we get the generalized form through fractal fractional derivative in equation number 16, 17, and 18. Next. This one is the definition of fractal fractional operator of Caputo-Fabrizio with power law kernel and defined as in equation number 19. And here N0 and N of 1 is a normalization of the function in which we get value 1. After applying the integral transform technique, in this one we use the Laplace transform, and we get equation number 16, 17, and 18 of the momentum equation, concentration, and temperature equation. After simplification and inversion Laplace transform, we get the final solution in the form of 16, 17, and 18. Next. Now result and discussion. We use Mathematica for the simulation, and we get the graphical representation by using this one. The alpha is actually the velocity profile against fractional order, and the beta is represent the fractal order. And we see that the both operator have variety of solution on velocity profile by taking other physical parameter constant. In this, we say that we conclude that fractional and fractal order derivative give us more realistic result as compared to the classical one. And by taking beta, which is a fractal operator, and in beta, we take the fractional operator alpha as a constant, so we get more realistic as compared to the fractional one. Next. This is the thermal Grashof number analysis and the mass Grashof number analysis. By increasing both the Grashof number, we get the enhancement in fluid velocity. This is due to the buoyancy forces. The thermal Grashof number enhance the buoyancy force, in which we get the increase in the velocity profile. Next. This is the volume fractional parameter effect on the velocity and temperature profile. By increasing the volume fractional of nanoparticle from 0.01 to 0.04, it means that we add 4% of 4% of nanoparticle in a base fluid. And we see that by putting these particle concentration is enhanced, and as a result, the velocity is decreased and the temperature profile is increased. Next. This is the volume fractional effect on the concentration profile, and the next in figure 9, the Schmidt number effect on the concentration profile. The volume fractional of nanoparticle increase the concentration in a base fluid, in which retard the concentration profile, and similarly the Schmidt number. Next. But the main purpose of the nanoparticle is to enhance the heat transfer rate. So in this paper, we also find the Nusselt number, which represent the heat transfer rate. And also we take the concentration profile, so we have the mass transfer as well. So by we can see that by increasing the volume fraction of nanoparticle, we have increasing in Nusselt number, and we see that the heat transfer is enhanced up to 3.62%. And in the next one, we see that the mass transfer is enhanced up to 5.68%. And this is the main application of the nanofluid, which enhance the heat transfer rate. Next. Concluding remark. The following key findings are the main finding of our present analysis. The fractal fraction operator give us a variety of results to best match the theoretical finding with the experimental survey. As I mentioned, that fractal fraction is more realistic as compared to the classical as well as the fractional one, because in fractional one we have one fractional operator, and in fractal fractional we have two. One is fractional and the other one is fractal. And the considered numerical algorithm is capable to analyze fractal fractional linear partially coupled PDEs. And it is observed that for larger value of fractal order, fractional order, thermal and mass Grashof number enhances the velocity profile, while the volume fraction of the nanoparticle velocity profile decreases. Next. Increasing the polystyrene nanoparticle volume fraction to 0.04 per, it means that we put the 4% of nanoparticle in a base fluid, significantly increase heat transfer rate of the system, which reach a significant increase of 0.362% after adding 4% of polystyrene nanoparticle, while the mass transfer rate is significantly increased up to 5.68% when we increase the polystyrene nanoparticle reach 0.04. Next. This is the future suggestion for the upcoming researcher, that one can use the different fluid. In this one, we use the kerosene oil-based fluid. You can take Maxwell fluid, Order B fluid, Brickman fluid, Jeffrey Walters B fluid, second grade fluid. One can take different nanoparticle that, and for different purposes, that silver, copper, gold, single wall, and multi-wall carbon nanotube. And different researchers can take these models for different geometry, like cylindrical coordinate, polar coordinate, spherical coordinate, circular disk, and thin needle and stretching sheet. And one can change the boundaries, as boundaries is also important, take an important role in the analysis. You can take oscillation, fluctuation, closed channel, Newtonian heating, ramp, and isothermal water temperature. Next. Thank you for your attention.
Any question or suggestion, everyone? And you? Okay, no question. Thank you for nice presentation. Okay, thank you so much. Next group.
Thank you.
Okay, for the next group, Miss Viparat and Sawarak. Okay, can start. Don't forget, open your camera.
Okay. Good afternoon, everyone. Our group has member is Miss Viparat Warapithong and me, Sawarat Jitngam. Today we will present in topics infinite product and its convergence in Cas1 space. Next. For the scope of our talk in 6 topics. The first one is introduction. The second one preliminary. Third one main result and application. Numerical implementation, and the last one is conclusion. First one is introduction. We will talk about in 1977, Brooks and West first introduced a strongly non-expansive mapping. Next one in 1982, Brooks generalized a strongly non-expansive mapping to strongly quasi non-expansive mapping. And the next one for example of matrix projection mapping. Next slide. Matrix projection mapping was studied in 2012 by Barkak, Searstone, and Sim. They proved the sequence like this, and the delta convergent to a point in C1 intersection C2 whenever C1 and C2 are cross-convex subset of Cat0 space. And in 2018, Choi, G, and Lim proved the same result for any kappa space with kappa greater than 0. And the second one is resolvent mapping. Jones and Mayer proposed the resolvent mapping of proper lower semi-continuous convex function in Cat0 space. In 2013, Barkak applied resolvent mapping to solve convex optimization in complete Cat0 space. This method is called proximal algorithm. That is the first one popular. In 2014, Barkak he improved the proximal algorithm to solve the convex optimization when the objective function is the sum of several load function when Fi is a proper lower semi-continuous convex function. And this method is called a splitting proximal algorithm. In the same year, he used to find mean median phylogenetics on tree space. Next, 2016, Kimura and Kosaka introduced a new resolvent on Cas1 space. In the same year, Espinola and Nicole developed proximal and splitting proximal algorithm based on the novel resolvent on Cas1 space. And in 2019, Kachimura and Kimura construct a new resolvent on Cas-1 space. And in 2000, เต็มแก้ว Kam Aim and Chai Panya use resolvent to study splitting method on Cas-1 space. And the next one is delta convergence was studied by Arisa Lopez and Nicole on 2014. They study about achieve new convergent result to approximate a common fixed point of a finite family of firmly non-expansive mapping in Cash-Kappa space. Then 2016, Riz and Salinas generalize the Arisa-Lopez-Nicolet result for Cash-Zero space to prove a delta convergent theorem and use their result to solve the convex flexibility problem on Cash-Zero space. And 2020, Khatizadeh and Mohabi study the delta convergence of iteration for sequence form by strongly Cauchy non-expansive mapping on Cash-Zero space. So their work has motivated from this one delta convergent Arisa-Lopez and Nicolet on 2015 and this metric project mapping of Choi Ji and Lim on 2018 and resolvent mapping from Espinola and Nicolet on 2016 with condition is complete admissible Cas1 space and intersection of arc-min Fi is non-empty. For preliminary is skip talk by Viparas.
For the preliminary, first one we will give about geodesic space that define the mapping gamma joining from X to Y with this condition and have distance like this. If D is positive real number, then the matrix space X is said to be uniquely geodesic. For each xy in X and distance between xy less than the positive real number, then there exists a unique geodesic joining X to Y. And next one, if we study X is uniquely geodesic matrix space, then the connected between X and Y is geodesic, and we will say it unique if we have only one geodesic to connect on X to Y. And we write this one, XY is a mapping here, gamma of form 0. This one is a mapping to denote a geodesic segment of Y. So in this case, this paper will use this symbol on Cat1 space. Next one is a geodesic triangle. Since we know before that in our space we have XYZ here, so XYZ in X we will have a geodesic triangle here, which this one is with a point here connected with this, and then the sphere defined by this one, where the product equal to summation of xi, yi. The sphere matrix space, we have a distance function here equal to this one, and by Bisson, he study in matrix space, then they define for any x not equal to y, then the distance of xy less than pi. Then we can say that this one has a unique geodesic from X to Y, given by this one geodesic gamma XY at T for any T in 0 and distance between X and Y. For the triangle inequality, for the triangle that we have geodesic triangle in the space X, and then it will call uniquely pi geodesic space X, which satisfy this condition, and then we can find a comparison triangle in the space such that the distance between xi, xj is equal to distance on a sphere. So next one, for the geometric joining xi to xj, and u is gamma at t for some t in our domain. Then a point u bar and gamma bar is called u bar is called comparison point, which u bar is mapping gamma bar at point t. With joining from xi to xj bar. And then for the x uniquely pi geodesic metric space, we satisfy this condition, then it will say that this space is Cat1 space, and a Cat1 space is called admissible if the distance between xy less than pi over 2 for all xy in X. Next one is convexity on Cat1 space. For the convex set, we will say that a convex C is a convex set if any xy in set C and the line connected between x and y is subset of C. Next one is talk about effective domain. That is the normal that everyone know that. And for the convex function, then we define on our space is Cat1 space defined by using this symbol less than or equal to 1 minus 1 f of x plus t f of y for every xy in x and t 0, 1. For the delta convergence, we study first by the sequence in the space X. The asymptotic center, we use this symbol, which defined by this, and the sequence xn will say the delta convergent to element z of x if the asymptotic center is equal to z for each subsequent xni of xn. In this case, we can say that z is a delta limit of xn. It means that if we have xn convergent to c, then the sequence xn is delta convergent to z. For the delta convergent to z, then it's bounded, and every subsequent of xni of xn has a delta convergent to z2. For the w delta of xn denote for set of all z in x, which there exists a subsequent xni of xn, which delta convergent to z. For the subset C of X, we will call the delta closed if for Y in C and the delta limit of some sequence Yn stay in the set C2. This is we will call delta closed. And the sequence Xn is said to be spherically bounded if satisfy this condition. In particular, if the dimension of X less than or equal to pi over 2, then the space X is said to be admissible, and every sequence in the space X is spherical bounded. So our space that we consider in this paper is complete admissible Cat1 space. For the first one, we study about strongly quasi non-extensive mapping. Started by the mapping T here is mapping from X to X, and fixed point T here is defined by this. Suppose that the fixed point T is not non-empty set, then if we have this hand from the mapping T from X and P less than or equal to the X and P for all X in X and P in fixed point of T, then we can say that the T is quasi non-extensive mapping. If T is quasi non-expansive mapping, and then every sequence xn in X and P in fixed point T, such that the supremum of distance xn and P less than pi over 2 and the limit this one equal to 1. Is follow that is mean that the limit of xn and the mapping T of xn are equal to 0. Then it's called, this one is strongly quasi non-expansive mapping. Moreover, in the sense of Kimura and Sato that he studied on CAT0, he said that the mapping T is delta demicode if for every delta convergent xn in X and its limit belong to fixed point T, whenever the limit of the xn and mapping T of xn are equal to 0. Next one is definition for orbital delta demiclose. In this case, we will study the delta, the convergence of delta demiclose and orbital delta demiclose. So we need to know the definition of orbital delta demiclose first. In our space and mapping T, the mapping T is called orbital delta demiclose if we have some X star in fixed point T and the sequence in the set X satisfy this all three conditions. Then we can say that the mapping T delta demiclose. And before go to the main result, we have very important two lemmas. The first one is if our same space, let XD be complete admissible CAT1 space and suppose that the sequence xn spherically bounded sequence in X and asymptotic center is singleton. Then the sequence has a delta convergent subsequence to the same delta lemma. This one is come from Espinola in 2009. For the second lemma is talk about the sequence xn is spherically bounded in the set X and the distance between sequence to limit, delta limit is convergent to every z, this one. In W delta is a set of all delta limit. Then the sequence xn is called delta convergent to element x bar in X. Next one is our main result. The first one is this paper want to set the product of strongly quasi non-expansive and delta demiclose mapping is also strongly quasi non-expansive and orbital delta demiclose mapping. And the second one, they prove the delta convergence of the sequence which construct by a strongly quasi non-expansive orbital delta demiclose mapping in the setting of the complete admissible CAT1 space, which they starting by the lemma, first two lemma to be the important tool in determining their result. The first lemma is in our space, the mapping TI map from X to X is strongly quasi non-expansive mapping for all I, and the intersection of fixed point TI not is non-empty set. Then the fixed point of the mapping T1 to Tm is equal to intersection of fixed point Ti. And the second lemma is say that for every Ti is strongly quasi non-expansive mapping and the intersection of fixed point Ti not non-empty set, then the mapping T is equal to Tm product with Tm minus 1 until T1 is also strongly quasi non-expansive mapping. So we have our main terrain is in our space, and our mapping is strongly quasi non-expansive delta demi close mapping for all I, and the intersection of fixed point of each Ti are non-empty set. Then T is a strongly quasi non-expansive orbital delta demi close mapping. And next one, we have that for the if our mapping T is strongly quasi non-expansive and orbital delta demi close mapping, and the set fixed point of T is non-empty set, then for any initial point x0 in x, the sequence defined for each n in n, the defined by the sequence xni equal to the mapping T to n at x0 is a delta convergent to element x bar in x in fixed point T. Okay, next one is the application. They will find the application of their result on an optimization problem to the two problem. The first one is convex minimization problem, and the second one is convex feasibility problem. For the first one, they study on our space, and the function is proper lower semicon convex function, and consider the resolvent mapping here is a strongly quasi non-expansive mapping and delta demi close mapping, such that the fixed point of the resolvent mapping is equal to argmin of x for all I. And for the feasibility problem, I will talk about this later. For the first one is convex minimization problem, and function here proper lower semicon convex function, and the resolvent mapping are with respect to lambda I greater than 0 for all I. If argmin of x is non-empty set, then any initial point x0 in x, then the sequence are defined by this is delta convergent to element x bar in argmin f. And the second corollary, we have that if our function defined like this, the summation of fi, where each function, if fi is proper lower semicon convex function for all I, then for any initial point x0 in x, the sequence xn is delta convergent to the element x bar equal to the argmin f. For next one is convex feasibility problem. They consider the subset C in X that for each Ci is closed and convex set. In particularly in case of, I will say that this particular case of convex feasibility problem. In our space, if we let C1, C2 to Cm be a non-empty closed convex subset of X, and then the convex feasibility problem is to find some point X in the intersection of the set closed convex set Ci, which this intersection are non-empty set. We have two corollary also. The first one that if the mapping, our mapping is metric projection mapping from X to X are closed and convex subset. From X to onto C, I for all I. Then the intersection of Ci, I'm sorry, this one is metric. Intersection of each Ci are equal to, not equal to empty set and non-empty set. Then for every initial point x0 in X, the sequence defined for each n in n, then define like this. We have that the delta convergence on the element x bar are equal to intersection of Ci. And the next one, if C, our subset C is non-empty closed and convex subset for all I and the intersection and non-empty set, and we have some Cj is a compact set for some j, then the sequence xn is convergent to element x bar is equal to the intersection of Ci. Next one is numerical implement of his work. We will give talk by Nong Em.
Okay, this part is about numerical implementation. This is the complete admissible class 1 space X and closed convex subset C1, C2, and C3. Figure A is the complete admissible class 1 space, and figure B is the closed convex subset C1, C2, C3 on X. Next. The result of the implementation of the alternating method to the approximate the solution of CFP. Figure A is this is the alternating sequence xn on space X. It start in X mark, back in projection, and sequence to X rate X mark. And figure B is the error after n iteration. And next, they change X mark, X back mark, and projects the same like figure C, the alternating sequence xn on space X. And figure D is the error after n iteration. And conclusion. In this paper, we introduce a new concept of orbital delta demi-cross mapping, which is a generalization of delta demi-cross mapping. And they have shown that the product of strongly quasi non-extensive delta demi-cross mapping is a strongly quasi non-extensive orbital delta demi-cross mapping in Cat1 space. They obtain more general convergent result to approximate a common fixed point of infinite product of strongly quasi non-extensive orbital delta demi-cross mapping on Cat1 space. The result can be applied to the minimization of convex function and the sum of finally many convex function, or to an abstract minimization problem, which allow the study of the alternating projection method for the convex feasibility problem for finally many sets in Cat1 space. Thank you for your attention. Thank you so much.
Any question or suggestion?
Hello. Hello, can you hear me? Hello.
Yeah, it's clear. Can ask them.
Okay. Thank you for nice presentation, Jia and Nong Em. I have a little bit question. Please go to the page 15. The definition of delta convergence. Yes, this page. Please check the definition of delta convergence again. Maybe I found some mistake. Yes, that you say if asymptotic center of xn right equal to set of C. Yes, please make sure that the sequence xn or sequence xni.
Okay, thank you.
Okay. Next, maybe on page 32.
32, right?
Yes, 32. The
Here.
query. Oh, sorry, 30. Go back. a little bit.
30.
30. Sorry.
Here.
Yes. What is the difference between these two queries? Because it's very similar, right?
Yes. So it's closely to similar, but they have some here condition that for some set C is compact set. The first one
Mhm.
is we have only the C is closed convex, non-empty closed convex subset. Here we add more one condition.
Yes, it is one of two different. One more difference between these two queries. You correct. The first one is the assumption is different, right? And the second one is about the result of this query. The first one, query for quality, say that the sequence xn is delta convergent, but the second one is say that the xn is convergent. Did you say you saw that?
Okay,
Did you-
I will.
yes, it is one more different point. And
Yes.
in the numerical part, when we use the query 4.4 because we know that the C1, C2, and CT is compact. And okay, thank you, Piyaja. And last question is about the numerical part. Maybe on the 32. Yes. Okay. Why you know that it on the picture A? Why you know that the space X is admissible?